All right. So we were looking at the last thing we were looking at yesterday was Fibonacci sequence, and we encoded the Fibonacci sequence. And what we observed is if you run Fibonacci sequence for say um, give me the first 30 Fibonacci numbers, it takes a while, right? So it's noticeable, and then it produces the results. That's fine, but really I would call this inefficient. In particular, this stream encoding has the same exponential behavior as the usual recursive Fibonacci encoding, right? And we know that this is not um, the the appropriate way to encode Fibonacci, right? So in your first assignment, you had also encoded Fibonacci sequence using tail recursive encoding, right? Um, and hopefully we can do the same thing using streams. Otherwise, all of this nice properties that we've seen, where you can take individual pieces, combine them, and do interesting stuff, they shouldn't be just an intellectual curiosity, right? They have to be usable in practice. So what can we do here? So what is it that we want to do, right? So abstractly, whenever I call fib of n minus 1, that internally has a call to fib of n minus 2, right? And fib of n minus 3. And I have a call to fib of n minus 2 here. So if I compute a fib of n minus 2 in either of these places, right, I should be able to use that particular result in the second call. So can I reuse the results of a particular function invocation if the function happens to be pure, which we know it is here, and the argument is the same? So if the function is pure and the argument is the same, the result should be the same, right? Can we do something where we can reuse the results? Is what we should be asking if we want to optimize this Fibonacci. Of course, the details are there, right? So you can use manually encode this and all of that. But the question is, can you still maintain this nice way of encoding Fibonacci, but still be efficient by reusing intermediate results? So we go back to our the thing that we had seen in the lambda calculus semantics, which is call by need reduction strategy. So just to recall, what does call by need reduction strategy do? Call by need reduction strategy um, does not reduce a particular does not reduce the RHS of an application unless it is really required, but also ensures that if the same expression is reduced twice, then we share the results, right? So we hadn't implemented call by need. We had only implemented call by name, but call by need is a variant of call by name where you tend to reuse the results of certain reductions, right? And it would be nice to have this as an OCaml feature as well, right? So in OCaml, I would like to save the results of execution previously seen, right, and reuse them. And this is what OCaml provides in terms of what is known as lazy values. So OCaml has a opt-in feature for call by need, and the feature is called lazy values, while the rest of the language is call by value, right? Which is also known as strict evaluation. OCaml has this opt-in lazy value call by need reduction strategy, which is what we are going to use in this example. So the lazy module in OCaml has a few different functions, but these are the core ones, right? So essentially, there is a type called alpha t. Okay, so that produces a lazy value, right? You can represent lazy values using this type, and you can force lazy values. What does forcing mean? Forcing just means that go ahead and evaluate this lazy value to reduce it to some value alpha. Okay, so you reduce that value to alpha, and if you force it again, if you've already forced it, you just reuse the result from previous invocation, right? So the idea is that if you force the same lazy twice, the first time you would actually go ahead and evaluate it. The second time you would just reuse the results from the previous evaluation. This has some strange semantics in the presence of side effects. So here is an example to just walk you through what happens. So we have this keyword called lazy in OCaml. Okay, so lazy is just a keyword. You can put lazy around a particular expression. The expression will not be evaluated. So what does this expression first do, right? So what I'm doing is I'm doing 10 plus 20, right? I'm doing 10 plus 20, but I happen to also print endline hello. So this is a nonsensical program, but all I'm doing is I'm computing 10 plus 20, but while evaluating this expression, I also print endline to hello, right? So if I don't have this lazy, what will happen is I print hello, right? Because of this print, and then this whole expression returns 30, right? So um, that should be straightforward. If I add a lazy around it, again, lazy is a keyword here, right? Lazy just stops the evaluation. So let's see what happens. When you evaluate this, what you get back is a int lazy t. So the type says that v is a lazy computation, right? And when you force this lazy, what you get back is an integer. In particular, what you get back here will be 30, right? You just got this suspended computation now. This should remind you of something that we have done earlier, right? Um, you can think of morally, this is very similar to doing something like this, right? V is a computation, right? Which when V is a function which when invoked returns you 30, but also performs the effect, right? It prints end line when you call this function, not before, right? In the same way, lazy gives you a suspended computation, right? This expression is not evaluated yet. When you force it, it will go ahead and evaluate. The only difference is when I force this value, say once, I get int 30. I also print the value hello. When I force it again, I've pre-computed the result, right? But I'm not going to repeat anything that I've done previously. In particular, I'm not going to repeat this print end line. So the second time you force it, you don't see the hello. So the effect, the act of computing the result is only done once, right? So that's the difference. And this is the difference between doing this and something like this. If you say convert this expression into a thunk like this, every time you evaluate it, you will get the um, print end line printed out. So just to show that this works this way, I've evaluated this function twice, so I get this twice. But with lazy, what we get is if the function is computed, if the lazy is forced once, right? You get hello the first time, but not the second time. You just get the result. That is all lazy is doing, right? So lazy just says evaluate the computation. If it's previously evaluated, just return the result. Okay, so we saw this analogy. We saw this comparison between lazy and this thunk, right? They have some similar looking features. So what we are going to do is we are going to sort of replace our definition of the stream data type from using thunks to using lazies, and we will see how it performs. Okay. So in order to see how it performs, the semantics is going to be the same. The only difference is going to be execution time, how fast the program goes. So I'm going to have a helper function um, that will help me measure time. So the function is I'm defining as time it, right? That takes some thunk f, right? And I'm using features from Unix, right? Get time of day is a Unix function. So if you sort of look at get time of day, look it up. It's the same function that I'm using in OCaml. So it returns the current time in as a floating point number, right? I measure the time before calling the function. I measure the time after calling the function. And then I subtract the time at the start to get the execution time. The execution time is in seconds. So I multiply that by 1000 to get execution time in milliseconds. And I also return the result. So what time it does is, given a thunk, it returns a pair of the result and the time it took to evaluate that function. And the reason why we do this is we are going to keep measuring time in the rest of the lecture, right? So just to show you that certain encodings are efficient. So that's time it, right? So it takes a thunk, unit to alpha, and then returns you a pair of alpha, and this floating point is the duration that it took for executing this function. Okay. So first, let's see um, whether a naive encoding works out, right? Naively, what I'm going to do first is, oh, I know fib30, taking 30 from the stream fibs is expensive. So let me just put a lazy around it, right? Lazy around the whole thing. So what I'm doing here is I'm getting the first 30 Fibonacci numbers. I'm reversing it. I'm getting the head, which means I'll get the 30th Fibonacci number, right? I'll return the 30th Fibonacci number, and I'm making this into a lazy computation. So I'm naively trying to make it faster. Let's see what happens. So if you do this, you get a computation, which is a int lazy.t. In particular, this is a lazy computation that will return you the 30th Fibonacci number, right? And now what I'm doing here is I'm calling this fib30 of lazy by timing it, right? I time it. So this will be the result of fib30 lazy, which is the 30th Fibonacci number, and this will be the duration of the execution. So I just print it out in a nice form here. So fib30 of something is this, and time is in milliseconds, right? So when you run it, it takes a while, right? This star thing is showing that it is evaluating. So we get the 30th Fibonacci number. We also see that it took 3.15 seconds, right? And because I have a lazy around the entire computation, and I force the lazy in the body, right? I actually force the lazy here. Because I've already run this once, now I'm going to run it again. The second time you run it, we get the same result, but you also see that it's much faster, right? Instead of 3.15 seconds, this took 0.36 milliseconds, right? So you can keep running it again. The time changes, but this is so low that it is just showing you the usual variance that you have measuring very small things, right? So it's much faster than the initial run. Okay, that's good. So given a particular call for fib of a particular number, if you ask for the same number again, then it's fine, right? Let's try the same thing with fib31 of lazy, right? So I'm doing the same thing with fib31 of lazy, right? And I'm measuring the time. So the thing that we are missing here, right? So it takes a long time. The thing that we are missing here is I've already computed fib30 of lazy, right? In the previous slide here. This fib31, which internally also contains a call to fib29 of lazy, right? Which is what I would require for fib31 of lazy, right? So essentially fib of 31 will recursively call fib of 30 and fib of 29, both of which I have pre-computed here. But I'm not using the results in any interesting fashion here. And this execution took almost 5 seconds, right? So by just putting lazy around the entire computation, we are not going to make it any faster, because I'm not reusing the results of the recursive calls. I am just reusing the results of the outermost call, right? So of course, if I run this particular number again, it will be faster. But if I ask for 32, it will be as slow as molasses again, right? So So we are not reusing the results of FIP30 in FIP31 here. So how can we make this better? So the important observation is when we perform the recursive calls, we are not reusing the results. We are just um, using lazy at the outermost level. So this is not going to work. So we need to embed lazy deeper into the definition of the stream data type, right? Which is what we do here, right? So I redefine the stream data type. So this is a redefinition of the stream data type, where I say a stream has the cons constructor, it has a value, right? The head value, and the tail is a stream. It's a lazy stream. It's a lazy stream of alphas. So recall that the earlier definition used to be unit arrow alpha stream, right? This is what we were working with so far. So morally, this is doing the same thing, right? So it's also producing a lazy computation. Sorry, it is also producing a suspended computation for the tail. But the important difference is that we are not going to repeat evaluation of any functions. If the free stream has been computed once, we are going to reuse the results for the same invocation again. That's the most important difference. Rest of the functions are going to look exactly the same, right? Head is just get the head of cons. Tail is get the tail, right? And instead of now we actually lazy force it. Earlier we used to call that function because it used to be a function. We now just force the lazy now to get the tail of the stream. Take and zip are just the same functions. So these are character to character, the same function as what we had used earlier. The only difference in head, tail, take, and zip is this lazy.force here instead of calling this function L. Okay, so now we have a lazy stream which internally uses lazy. We've defined all of these four functions because these are the four functions that I'm going to use for Fibonacci. So I construct the fib lazy stream, right? So again, this is, I just use a different name. This is alpha equivalent to the previous definition of the Fibonacci stream that I had, right? Now this is much faster. So I'm actually doing 100, right? Take the 100th Fibonacci number, give me the 100th Fibonacci number. This is going to be very fast. This took 0.1 milliseconds. Recall that even 30 took some 3 seconds or something, and then 31 took 5 seconds. This is 100, and it goes very, very fast. The reason is that all of the recursive calls that we had are being memoized, sorry, are being cached and reused. So, so what is happening here is we are as efficient as writing a tail recursive lazy or your tail recursive Fibonacci or your Fibonacci description with two variables, right? Which is what you will do in C. So there is a question. I was going to stop here anyway. Sir, in the definition of the stream, what is the meaning of adding lazy.tree after the stream? So that's the type, right? So so any lazy computation, right, has the type alpha lazy t, right? Whenever you wrap something with the lazy, the thing that you get back is a integer lazy. So if I do something like lazy 10, I get int lazy, and when I force that, right, lazy dot force of v, I get 10 back. So all the type says is it is a lazy computation which when forced gives you an integer, is what the type is saying. Does that make sense? And the reason why this is so yeah, so you're asking about this. So the way to read this is the type stream, right, contains a single constructor which has the head value alpha, and the tail is a lazy stream, right? So it's it's a computation which, when forced, gives you the tail of the stream. That's the way you have to understand it. And the reason why this shows up is we use lazy here, right? Just look at the definition of this. We use cons1 lazy, cons1 lazy. Our earlier definition of Fibonacci stream used cons1 thunk, right? Because we had used thunk as the way of describing suspended tail computations. That's the difference. Does that answer your question? Okay. So the second question is, sir, is saying that the stream is lazy different than saying that each element is lazy? So we can define it as the stream is lazy, right? So the each element is not lazy. So the way we've sort of encoded this is in the same way we've sort of suspended the tail, right? So we've sort of said the tail of the stream is a suspended computation. When you need it, you actually invoke it. We are just suspending the tail of the stream using a lazy. Okay, so any question that you can ask about lazy, you can also ask about this definition, right? And for the same reasons we came down to using a thunk for the tail, we are using lazy. There is nothing else that is different, but lazy is internally giving us the reuse of cached results. Does it sort of answer your question, Sarthak? Rephrase your question, right? You ask yourself the same question that you're asking here using the previous stream definition, right? And I think if you can answer that, the same answer will be the answer here. Okay, so good. So we got this one to be much faster. And okay, that will be. Okay, yeah. So this is faster, and this is as efficient as writing writing the usual tail recursive function that you had written in assignment 1. So okay, so I use this one word which I sort of quickly took back. I use this word called memoization, right? So, and I said, okay, I take it back. Lazy values in OCaml are a general idea, fit in this general idea in programming called memoization. Memoization is a fancy term, but all it stands for is caching, right? So if you have a pure function, you and the function, because it is a function, it's a mathematical function. You give it some value, it will return some value, right? Mathematics, you don't if you're just looking at the semantics of the function in terms of what it does, you're not going to worry about execution times. But when you write programs, you do worry about execution times. So the idea is that if you have a pure function, if I give it some result, after a lot of time it returns some result, I can just cache the result. I can store it in a table, right? Input and output pairs. And the next time I get the same argument for the same function, I can just return the result immediately, right? So this is an idea which is called memoization. And lazy values in OCaml are a specific implementation of this, right? So there are some details which makes it very efficient to implement lazy values in OCaml. They are embedded deeply in the compiler. But this whole idea, right? This is just caches attached to pure functions, right? And let's see how to build this ourselves, right? So the idea itself is interesting, but it's not too complicated. It's just the idea of saying, okay, if you give me a pure function, I'm going to attach a cache to it, and this cache will record the previously seen arguments and result pairs, right? So we can do this very nicely in OCaml. So that is what we'll see in the last part of the lecture. Okay, so we are going to define this function called memo. And the idea is that if you give me a pure function, any pure function, right, some alpha to beta, I am going to attach a cache to it. So I'm using a hash table here. You've not seen hash tables in OCaml, but hash tables are just the hash maps or other things that you might have seen in, say, C++, right? So what are hash tables? Hash tables um, are going to give you, it's a data structure with a key and a value, right? And you can insert and remove these entries. If you look up with a key, you will return the same value as seen before, and it's generally efficient. So it's um, most operations happen to be log n, right? So that's the advantage. There are details are there. So we have a hash table in OCaml as well, right? So what I'm going to do is, because I'm attaching a cache to a function, I'm going to create a hash table and then attach it to this function. So how do I do this? I first create a hash table. The 16 is a number that sort of signifies the initial size of the hash table. The hash table size is just a initial recommendation, but it can keep growing. So you don't have to worry about sizes anymore. So that's the cache, right? And I'm going to return a new function, right? So memo is going to take your current function from alpha to beta. It's going to return a new function from alpha to beta, right? Which has this internal cache attached, so that it is going to look up the arguments first in the cache. If the value is already, if the argument is already in the cache, then the value is going to be the result. It is just going to return that. If not, it is going to compute it, add that entry to the hash table, and then return the result, right? So this is what we are going to do. And since we are defining a new function, I define a new function here, right? I'm defining it as an anonymous function. So given a value, right, you first look up in the hash table whether that value is there or not. So for this, we are going to use hash table.find option. So find option gives you none if the entry is not there. Find option gives you some result if the entry is there. That's the value that we look up. So I look up the hash table cache with the key v. If the key is there, right, I already have an entry for that particular argument, then the value that is associated with that will be the result of the computation. So I just return the result here. If not, maybe you've not seen this value previously. What you first do is actually call the function, the original function f, with this value, right? So you get a result. So I got the result now. You add to the hash table, right, this cache, a pair of, this is the key, the value, sorry, the key, the argument, and the result. So now the hash table has an additional entry. And then you return the result that you computed. So hash table is a mutable data structure, right? So it has, um, it if you add it, it destructively updates the hash table. So you don't need to keep passing it around or anything. But all we've done here is we've attached this hash table to this function, right? Now, whenever you call the resultant function, we are first going to look up in the hash table. If it is already there, just return the result. Otherwise, we're going to first compute the result of this function invocation, add an entry to the hash table, and then return the result. Okay, so as I suggested earlier, memo is a function that takes any alpha to beta function and then returns an alpha to beta function. So imagine there is a bracket around that, right? So even though it is written this way, it's like you take some function and it's going to return a function. The only observable difference between these two functions is going to be the execution time, because we have a cache and the presence of side effects. Any questions regarding this definition? So I'm using hash tables here, but it should be fairly straightforward, the use of these functions. No questions. Okay. So now let's use this memoization for something interesting, right? So let's see whether this is useful in practice. So here is uh, here is a spin function. So all I'm doing here is, given a number of iterations, I just loop for so many iterations. This is just to add some time. Okay, so spin is a recursive function. If n is 0, then it simply returns unit. Otherwise, it recursively calls spin with n minus 1. So it simply adds some execution time, right? It's just a tight loop. So it takes a number of iterations and does nothing useful except it spins for a while. So I define an expensive identity function, right? This expensive identity function spins for a little while and then returns the same value, right? So the type is going to be alpha to alpha, right? The type is the same as identity function, except that this will be really slow. Okay, so it's going to spin for a while. So now let's time this function, right? So I'm calling time it on this expensive ID. I'm going to get the result, which is not interesting. And I'm going to print the duration. So let's see how long it takes. It'll take a few seconds. So it took 3.6 seconds here, right? So because I had called this function with 10, because that is an identity function, I get 10 out. That's not a surprise. It just took 3.6 seconds to execute. So now let's memoize this identity function. So what I'm doing here is I memoize this function, right? So I get a new function, which I call memoized expensive ID. And the difference between this function and this original function is that now we have a cache associated with this function. But if you look at the type of this one, it is weak because of weak polymorphism that we had studied earlier. I'm not going to go into the detail, but it's still an alpha to alpha, right? So that's the observation here. Don't worry about why this is a weak. The short answer is that this is an application and it has arbitrary effects. In particular, it builds a hash table internally, and that is why this function cannot be in multiple types. You cannot apply string ones and integer ones because the hash table will contain string and integer, and we don't like to mix types in OCaml. So, so this weak polymorphism is necessary here. Okay, so that's fine. So now let's call let's time the memoized expensive identity function with the same input 10. So the first time we are invoking it, it still takes a lot of time. In particular, it took almost the same time as previously, right? 3.655, 3.681 seconds. But the next time you call it, it's going to look up the value 10 in the hash table, right? And it's the value is going to be there in the hash table. So it's going to return very fast. So we got the result back in 0.01 milliseconds. Right? So this is how memoization works. Of course, the hash table keeps growing inside. What we are doing is we are trading off space and time, right? So because this function is really expensive, we are adding a table. We are using extra space in order to trade off time. This is not like a perfect cache, right? I mean, this is not a cache that you would want to actually use in practice. In particular, this keeps growing. So if you have, say, 1,000,000 values, the hash table is going to contain 1,000,000 elements. We don't have cache eviction policy or anything. I think you might have studied cache eviction policy in computer organization. So we want something like that earlier. The actual implementation of something interesting will have to do all of that, but that's not the point here. We sort of built something that works. So let's use it in more interesting fashion, right? So the function that we have here is a non-recursive function. So we memoized a expensive ID, right? And this is a non-recursive function. So that memoization works nicely. But it turns out that memoizing recursive function is quite tricky. For the same reason why this using a lazy in Fibonacci stream was a little bit interesting. Memoizing recursive functions is also a little bit tricky. So in particular, we need to do this idea called tying the recursive knot. I will slowly lead you on to the problem. So let's start with a simple recursive function that we all know how it works, right? And then we'll slowly see what is the problem, and then we'll come up with the solution of memoizing recursive functions. Okay, so here is the usual definition of Fibonacci, right? Recursive Fibonacci, inefficient one. Um, we know how this works, right? So if you do fib of 40, it's going to take a while. I don't know how long it's going to take. Okay, 7 seconds. Okay, 7.7 seconds. And it returns the result. So let's do what we've done previously for expensive ID, right? Let's just memoize the Fibonacci function. I'm just going to call memofib, which presumably what it's going to do is return you a memoized version of Fibonacci, which internally has a cache, right? So let's try to invoke this function. So here is a memo of, let me run this memofib. Here is memofib of 40. So this is going to take a little bit of time, the same as what it had taken earlier, almost 7.7 seconds, right? Because I memoized 40, if I ask for the same value again, it gets me the result really fast, right? 0.009 milliseconds, right? So that's quite fast. But if you sort of look at the structure of Fibonacci, right? When I call fib of 40, I'm going to call fib of 38 and fib of 39. If the function were memoized, does it mean that the recursive calls have also been memoized? It turns out it is not, right? Because we are attaching memoization at the top level. So if you call fib of 39, it's going to take a lot of time, right? So this is taking 4.9 seconds, even though fib of 40 calls fib of 38 and 39, which internally calls fib of everything. When I call memo fib of 39 just after memo fib of 40, it still takes a lot of time, right? If you run this again, it goes faster because there are two entries in the hash table now, one for 40, one for 39. The problem, what is happening here is this memo fib, right, is only memoizing the outermost call. So when you call with 40, it is looking up 40, right? And then it says, okay, initially there is no 40, so I'm going to call it. It's going to compute the result and it's going to store 40 and the result, which is this number in the cache, right? But it hasn't memoized any of the recursive calls. Any of the recursive calls are still going to be calls to the original fib function, right? So this is completely missing, right? So so that is why even though fib of 40 calls fib of 39, we are not reusing the results here. This is undesirable, right? So ideally, you want to memoize all of the recursive calls as well, so that instead of this being exponential, this is actually linear. So there are only linear number of calls. So we keep reusing the previous results. So how can we do this? So abstractly, right, what is happening here is whenever I create this memoization function, I only memoize the outermost call. I don't memoize any of the recursive calls. So how do we do this? So let's stop here. So do you get a sense of what the, yeah. Okay, so Sarthak has a good point. So if we had a global cache it would not have been a problem. No, it would still be a problem, right? Because if you think about it, when I call memo of fib, right, what does a memoization function do? The memoization function calls fib here, right? Fib of 40 here, and fib of 40 internally is going to call fib of 39 and fib of 38. Those are not memoized, right? What has to happen is that the memoized version has to recursively call the same memoized version, right? So abstractly, I don't know why this went all the way here. Lazy string. So this memo definition, right? So we have this definition. So this wouldn't be solved with a global table because when I memoize something, I add something like do memoization, right? And then do memoization. And just sort of writing it down abstractly to say, here we check for the entry n, right? And then if it is there, return the result. Otherwise, go and compute this function, right? This is not actually calling the memoized functions. The recursive calls are all on the original function. Ideally, we want all of these to be memofib, right? This needs to be memofib. This needs to be memofib. This needs to be memofib. I mean, you have this chicken and egg problem now, right? So we want to define the function memo independently of everything, right? And we want recursive functions to use memoization. But we have this chicken and egg problem because the definition of recursive function itself needs to be aware of the fact that it is going to be memoized. I mean, this is the problem of what I mean by tying the recursive knot, right? So yeah. So thanks for that question, Satak. Help me answer it even more. So that's the problem, right? Even adding a global hash table will not fix this problem because the recursive calls are still happening on the non-memoized version. How do we fix this? Of course, we have a way to fix this. So it's a bit, and again, this is harking back to the ideas that we've previously seen, and we are going to combine a few interesting recipes that we've seen so far. In particular, right, the first technique that we are going to use is we are going to use an encoding that we had used for passing functions to Y Combinator, right? So recall that when we looked at Y Combinator, we had this explicit function, right? This function is sort of describing a Fibonacci function again, right? But it's a non-recursive version of Fibonacci. The idea is that this function argument, just like we had seen in when we used Y Combinator, we will use this function f to be the recursive version of the function that we are defining here, right? So the recursive calls f of n minus 1, sorry, on n minus 1 and on n minus 2 are going to use this function. The idea is that somehow we are going to create a recursive version of this non-recursive function, which will be passed to this f, and we are going to invoke it here and here, right? Somehow. This is precisely what we had done in Y Combinator. Whenever we wanted to use an Y Combinator, we had this extra argument, right? Where we said any recursive function takes this extra argument, which will be the recursive version of the function that you're defining, right? That's the first idea, right? So, yeah, so we are observe that the original recursive function simply names, if it is fib here, it is just fib here. This fib norec names the function, but also takes an extra argument. This will be somehow filled in with the recursive version of the function that we are defining. Okay, so that's the idea there. So the way we tie this thing, right, we fill this in, is we will use a reference. We will use a or mutability features in the language to tie the knot. Okay, so this is perhaps the one of the most complicated programs, that 3-line programs that you'll see. So we will walk through it, and I'll hopefully try to explain it. But I also want you to sort of go through it in your own time as well, right? So our problem is we want to memoize recursive functions, right? This also memoizes all functions, irrespective of whether it's recursive or not. But anyway, so here is how we do it. So we define a function called memorec, right? That takes a non-recursive version of a function, fnorec, right? Which has to be in this structure. If you want to define a recursive version of Memoize Fibonacci, you have to define it like this. So you define a function name, it takes an additional argument for the recursive call, right? But internally the body is going to look like this, right? So that's the expectation here. So fnorec is such a function, right? First step, as a first step, what we are going to do is we are going to create a reference called fref that points to a dummy function. This dummy function is not going to be invoked, right? So let fref be this reference. That's a reference to a dummy function that takes some argument and then says assert false. If you ever are able to call this function just terminates the execution, right? It just stops the execution. So in the first step, what we've done is we created this fref variable that points to a reference to this dummy function. I represented functions with this parallelogram, right? And I have a stop sign just saying that this function should not be invoked. That is what has happened in the first step, right? In the second step, what we do is we memoize the function, this fnorec function, where we use the reference, where we use the function from this reference. Okay, so let's do this step by step. So I create a function called frec memo. The idea is that this frec memo is the memoized version of the function that we want to define. Okay. What it's going to do is it is going to call memo on this function, right? What is that function? It's going to take a value, some argument x. It is going to call this function that is passed, right? The original function that we want to memoize. Simply that fnorec. For the second argument, right? This argument here. So the argument for the recursive call, what we are going to do is we are going to dereference this reference that we defined in the first step, right? That is going to be a function, which is what we are going to pass as a recursive argument. And we are just going to pass the original input function x, sorry, the value x as the argument. And this would fill in the n here. So the observation is that we are somehow going to dereference this. The important observation is we are not dereferencing this fref yet. This function is going to be dereferenced only when you call it, right? Because we have put this in an anonymous function. Only when you call this function is it going to be dereferenced. So what is happening here is we created this frec memo function, this frec memo function, right? That's a memoized version of the original function, which internally refers to this reference here, right? This fref here, which is what this is pointing to. It is pointing to this reference, right? But it is not dereferenced yet. The idea is that if you dereference it now, it will actually point to this function that should not be called, right? This function, but we are not dereferencing it. Okay. So we have a memoized version of the original function, fnorec function here in frec memo. And the last step that we are going to do is update this fref reference to point to this recursive function that we've just defined, right? So what is happening here is we are going to update this reference here, the square reference, to point to the same one. So this is what we've done by tying the recursive knot. So ideally, what has happened here is, if you take a step back, right, from the code, we have memoized the original function, right, where internally every call to the recursive argument is going to be the same function that we have just memoized. And that is what is happening here. Of course, the details are all there, but at the high level, that is what has happened. So we've memoized this recursive version of this function, which is written in this very specific way, right? It takes the recursive function as an argument, the first argument. So we have memoized that function, and we've said that for the first argument, because we've updated fref to be the function that we've just memoized, we've tied the recursive knot. And finally, it looks like this, right? We dereference this function every time we recursively call it, but it's going to point to the same function. And actually, this variable is no longer required. The thing that we return is frec memo. We return this memoize function. So what we started with this is this fnorec, and we used a reference here to make this function recursive, but also memoized. Okay, so it's a little bit mind-bendy, so it's okay if you don't get the details of this implementation here, but it's combining multiple ideas that we've seen previously, right? It's combining the fact that you have a memoization, you have references here to tie the knot, we have recursive functions, we have ideas that come from what we saw in Y Combinator with this additional recursive argument. We put them all together to create a recursive version of memoized version of a recursive function. I'm not going to keep repeating the same words because that will just confuse you even further. But I just want to show that this actually works in practice, right? So once you have that, you can memoize the recursive function fib_norec, right? Memorec. I need to run this. So yeah, okay. So the type is not important. So anyway, so here is I've not defined this. So this is fib_norec. Okay, and then here is the memoized version of the Fibonacci, the recursive Fibonacci, right? Recall that this earlier took around 7 seconds. Now, because we are actually memoizing each of the recursive calls, when you call fib of 40, you would call fib of 38 and fib of 39. Since the cache is empty, you would call fib of 39. That goes through all the way and then comes back. You save the result in the cache. For fib of 39, you would have two recursive calls, right? That would be fib of 38 and fib of 37. Both of these are previously computed. So it turns out that the execution time is linear with the memoization. Of course, the constants are very large, but that's not the point, right? It has come down from 7 seconds to 0.09 milliseconds. And similarly, fib of 41 is also really fast. It is actually using all of the results from fib of 40 as well. This is not even linear. This is like constant time, right? It has 39 and 38, both of which have been previously observed. And yeah, and that's how you memoize a recursive function. There is one last example that uses this, but we'll have a look at it tomorrow. I've already taken 5 minutes of your time. If you have any questions quickly, I can answer it. Otherwise, I'm happy to answer questions in the next class. I'm not going to ask you to write this program in the final exam or anything, right? So no need to try to understand the high level ideas. Um, but yeah, but this is just not a thing that I would expect you to come up with in an exam or something. Okay, so take today and tomorrow, right? And on Friday we'll just pause for questions. Then I have one more example. This is on edit distance, and the idea is that memoization actually captures dynamic programming quite nicely. So what we've done here is dynamic programming, right? So um, the idea is if your function is pure, you can have the description of the problem as recursive description and make it as fast as a dynamic programming problem without having to explicitly do all of the bookkeeping required for dynamic programming. Right. So that's the idea here, and um, we will see that work in a real example where you do edit distance computation. I'll stop here. Thanks very much. Bye bye. See you on Friday.